Hello friends, we are back with digital control, and in this case we shall be seeing how we step by step change our approach in going in for a digital computer loop instead of a regular analog controller. And we see over here, as you can very well take the stock of the things, that we have a process. We normally take a feedback from the process, making use of some kind of sensor, and that sensor invariably has to have some transducer built in it. So this electrical signal, it goes to the controller where it is compared with the set point. The error is generated, and that error ultimately acts upon as per the instructions of the controller. The output is given to some sort of electropneumatic controller, or you can say electromagnetic converter, because this controller is normally giving us 4 to 20 milliampere signal, and this electropneumatic converter gives us 3 to 15 psi. And this pressure, it acts upon the final control element. Most of the times it is a kind of control valve which provides the necessary manipulated variable which acts upon the process to keep this controlled output at set point, in spite of the fact that you might be having some external disturbances which may be acting on the process. So this is a regular feedback loop with analog controller. Every signal is analog, that is continuous. Only thing is that at some points the signal may be in the form of current, at some points it may be in the form of pneumatic pressure, and some point it may be in the form of some flow, and all these things, they are happening continuously over here. Specifically, this controller is analog, that is, it's mostly making use of things like op amps, as we have already discussed in the previous course how we can make use of op amps for realizing PI or PID control. So over here, as we see, we shift over from the analog controllers to digital controllers. So we have to have some kind of computer to take care of the digital control. And we just cannot put any computer. We have to have the computers which are used for process controllers. This kind of computer, or these kind of computers, they must have the features, as we will be discussing these around four features one by one. The first one is the hardware. It has to have a floating point processor for fast processing. We just cannot go in for the slower processing because we are sampling the inputs at a very fast rate, and then we are processing these inputs at equal fast rate. We are outputting them at the same fast rate, and this processing and outputting must be done before the next sample comes. So if we are sampling, let us say, at the rate of 1 kilo samples, that is 1000 samples per second in some crucial cases, it means that we have only 1 millisecond. The entire thing, from taking the input, from processing, from giving the output, it must finish in less than 1 millisecond. Say the sampling time is not so rigorous, sampling time is, say, 4 samples per second, which is the case in most of the process industries. So in case we have 4 samples per second, it means that we have a fixed time of 250 millisecond for acquiring the data, for processing the data, for computing the error, for computing the output, for giving it to the output P to I converter. So all this must finish in less than 250 millisecond, and this 250 millisecond, it means actual 250 milliseconds in real time. And that is why we have to have one real time clock to keep track of the real world time. It is not a simulation, it's a real thing, real process working in the real time. That is why it has to have a real time clock built in it. What if the power fails? What if the computer system develops some kind of error and it shuts down? So before it shuts down, it has to transfer the control to some sort of backup control. That backup control can be in the form of device, that can be in the type of a system, or that can be another computer. So everything has to be kept in mind that in case of any failure, the process must not shut down on account of failure of power to the computer or because of some element not behaving in the system. So it has to have a proper power safe, you can say power fail safe automatic restart to take care of all these situations. Now what happens, many a times there is a bug in writing the software, and because of that the software it goes into a kind of endless loop. And you know what endless loops are. Suppose you go in for a kind of loop where it is moving and the breakpoint is never achieved, so it will just keep on rotating in that loop for infinite number of times. So to avoid that kind of situations where you say the system gets hung up, so to hanging of the computer it may take place, to avoid that we have to have a special kind of timer, and that timer is called watchdog timer. It detects the never ending loops or the hung up states. So once the computer that has these 4 points, then and only then it qualifies to be used as a process controller, because process control is something sensitive. We are controlling refineries and we are controlling cement plants and we are controlling big chlor-alkali things and paper and pulp kind of stuff. We don't want that computer should fail on account of any of these things, and we don't want the whole process come to crumbling stand still, resulting in loss of millions of rupees, which I think it's difficult for me to express. I've been visiting to number of places. I see that how crucial the element over here for control making use of computers is. Friends, once we make use of digital computers, the simplest thing which we can do is what is called DDC. DDC is direct digital control. Direct digital control, what happens in that case, if you compare it with the previous situation over here, the only thing which has changed is this portion. The controller is now digital. Since the controller is digital, and the output from the transducer which was coming over here, that was analog, so this C stands for continuous. The signal over here was continuous as in the previous case. It goes through a sampler. I think you all know what a sampler is, and it gets converted into the discrete signal, and that discrete signal is again given to A to D converter, which is nothing but analog to digital converter, and that gives the output in the form of a digital form. And this digital output is going to the computer control program, and this computer control, it's comparing the value of this digital feedback taken from A to D converter with the set point which was given by the operator through a kind of typewriter terminal, and the error is generated, and the error is then it's computed in terms of some PID algorithms which we will be discussing in due course of time. And these PID algorithms ultimately they generate the output, and this output goes to D to A converter. So we have the digital form, and then finally with every D to A converter, you must have studied in some other courses, we have to have a kind of hold element. And once we have the hold element, this digital signal which was converted into discrete signal gets converted into continuous signal, and thereafter the same old story takes place as it was in case of continuous controllers. So friends, as we can see that since we have replaced the analog part of controller with the digital part of controller, so all those things which have taken place, which we have selected over here in the smaller box and in the bigger box, these are the things which we have replaced, and we have to write a simple computer control program because the best thing is that this process has only single input and this process has only single output. It is one simple single input single output program, but then this computer is too powerful to handle only a single input and single output. It is seldom used as that. Normally it's able to take care of number of such distinct processes where you have distinct input and distinct output. They may not be memos, they may not be having any interaction. They may be like you are controlling the temperature and then you are controlling the level and then you are controlling the process pressure of a boiler, for example. These are the distinct loops, more or less distinct loops with very little interaction. But then instead of employing three controllers, we go in for a single controller. So that kind of cases we take to utilize the power of this digital computer control. So this is what we are going to see in the next slide. As you can see over here, so we have two distinct control loops, and since these are the two distinct control loops, we have to have make some changes in the hardware. So you see that the process has two final control elements. It is taking two feedbacks, and these are the two distinct processes. Over here we have two measuring sensors, two transducers, but over here we have a kind of multiplexer, and you all must be knowing what is the time division multiplexing. So it is first connecting to the upper part, then to the lower part. It's connected to the upper part, it's going to the first kind of loop, and then we have, as such as we had earlier, we had sampler and a to d converter, but we have just added one multiplexer over here at the input, and similarly we have added one multiplexer over here to the output. So this computer is also having some changes in the software. Earlier it was having only one control program. Now it has two programs, one control program for loop 1 and one control program for loop 2. So when it is controlling loop 1, then in that case you can see the signal is connected. As you can follow the laser over here, it is going from here, it is coming from here, and it is just moving over. And at that point of time, this point a multiplexer is connected with this, and then we have sampler. So this is coming over here. At that point loop 1 is being executed. When loop 2 is getting executed, in that case this multiplexer goes down and this multiplexer goes up, and we have the loop which is coming over here, the loop which is coming over here, and it's coming down to this point, and this point is connected over here. So this is the second loop, and for second loop the second program is executed. And to have a proper coordination between when loop 1 is to be connected, when loop 2 is to be executed, and when loop 1 is executed, what should be the position of two multiplexers. When loop 2 is getting executed, what should be the position of two multiplexers. That is all given by the coordination subprogram. So this is the way we can have a direct digital control in case of two distinct control loops, and we have noticed the changes which we have to bring about in hardware as well as in the software for this type of digital control loops. You can see we have yet another kind of control which is called supervisory control. And in supervisory control, what this computer is doing, this supervising computer is not controlling each and every element of the plant independently, but it is just giving a set point. It is giving a set point to first control loop, and it is monitoring the output of first control loop. Similarly, it is giving the set point to second control loop, and it is monitoring the output of second control loop, and so on. You can have third, fourth, fifth. You may have n type of local controllers. These local controllers can be analog controllers. These local controllers can be digital controllers, preferably if they are digital controllers. And ultimately they are receiving the set point from the supervisor control, and they're giving their output that this is the way we are behaving. So this supervisory control is creating a kind of data log and is having an overall supervision for the plants, and these are specifically done for the plants which are spread over several kilometers. Like for example, you have some pipeline, or you have some kind of gas fields where gas is being extracted from various wells, or oil is being extracted from various wells, and then all these things may be spread. Or in case of grid, as you see, the grid is spread over miles and miles and miles, so you have to have some kind of supervisory control where you have large number of controllers, so all are getting supervised by one supervising computer. Friends, this is how we implement the digital computer loops in industries. But in addition to that, we shall also be studying in due course of time what is called distributed control system. Right now, we have just focused on the direct digital control, what we call it as DDC, and we had just a glimpse of what is called supervisory control. But then, in due course of time, we will be going for what is called DCS, or distributed control systems. What is the philosophy of that distributed control system? What is the architecture of distributed control system? What is the advantages? What are the advantages of distributed control systems? All those things we shall be studying in due course of time, not in this session, but I'm just giving you a glimpse of how the things move from one DDC to two DDCs to n number of DDCs to supervisory control, and finally we will going for DCS. And then there's a small portion of it which is often part of DCS, or sometimes it becomes an independent control also, which is called programmable logic controllers. So we should also be discussing and studying PLCs. Perhaps we'll be going in for a course in a small session on PLCs. We will have hands-on experience also on the PLC controllers, how to program the PLCs in ladder logic. So all that will be done. Along with it, we will also be discussing distributed control systems. So this is all covered. Everything comes in digital computer loops. That is the overall umbrella of the digital domain. And we shall also see the things how we determine the stability in case of digital controls, how we go in for design of the controllers. We have issues like ringing of controller and so on and so forth. So those also will be dealt with in separate sessions one by one. I hope you have now a fairly good idea what digital computer loops are in general. In case you have any queries about these digital control loops, you can always contact me through WhatsApp, through phone, through Zoom sessions, or maybe, God willing, through our face to face interactions. I hope you have enjoyed these sessions. I thank you for being with me. I hope you stay safe and enjoy learning in journal. Thank you once again. Bye bye.